Alrighty, so time for last time mentioned we were going to some of the math. Next time that was a bit of a lie. We're going to take a quick trip into quantum entanglement just for a moment. Just because I feel like it might be worth covering, just to finish out all the non-mathematical bits of quantum entanglement and quantum mechanics. Because this is basically the point at which everything beyond is math. But that there's not really much to this, which is why this is going to be relatively short. Anyway, quantum entanglement. May have heard a lot of things about it, or not. But we're just going to start from square one. So, first things first, we have to remember the quantized spin from a while ago. So if we have like a particle, emitter, and we have, say, some set of magnets, for example, I'm ignoring all the poles of the magnets, just make this simple. As you might recall, the particles, if they're electrically charged, of course, they will have a random probability of either being deflected upward, which you call the up spin, or of being deflected downward, which we shall call the downward spin. It's very simple, and they'll never have a value in between those. And as far as the quantum theory goes, both of these values are randomly decided, and it's not very well written, but you can tell what it means. So it randomly ends up being either an upward spin or downward spin. And this is very important for quantum entanglement, as we'll see in a moment. But all this is important to get over first and foremost. But instead of having this whole setup for a moment, I'm just going to, from here on out, I'm just going to revert particles by their spin. So we'll either have like a spin upward particle, or we'll have a spin downward particle for simplification. And that's it. That's all there is for now. It's just that you have either an upward particle or downward particle, and as far as it goes, it's random as to which one you'll get. And why is this relevant to quantum entanglement? Well, if you've heard anything about it, this will play heavily into what you may have heard. So entanglement, we kind of say particle A and the particle B, and they can get entangled by some manner. And I think they have to be interacting with each other first. So you have to anyway, in order to make this work, for example, we can have, say, particle A and particle B in some sort of collider, and we can smack them at each other, for example. And because of stuff that I won't get into because math, these will now become entangled particles. A will be entangled with B. And what does it mean for them being entangled? Well, if you recall from the story of up and down spin, if we have particle A and particle B, and we pass them through the little detector, for example, we have the box, send them through, if particle A is upward, then particle B will always be downward. Or, reversed. If particle B is upward, then particle A will always be downward. And this is true, regardless of how far they are separated. For example, if we have, say, I don't know, Alice, I choose particle A, and we have, say, Bob, and here's particle B. If, for example, Alice were to send her particle through the machine, and let's say that she measures it to be upward spin. Well, when Bob sends his particle through a similar machine, that can deflect the particle, it will always be downward spin. This is true even if they're far apart. And you may have heard something like quantum entanglement is faster than light travel or instantaneous stuff, and you might wonder where this has to play in this. But you have to remember that in our quantum theory, at least the popular one, is that all of this is random. Like the upward spin is supposed to be random, and downward spin is supposed to be random. But at least for Bob's particle, Bob's particle is not random. Because it's determined by Alice's particle. Or if Bob were to measure his particle first, then Alice's particle wouldn't be random either, because it would depend on Bob's particle measurement. But obviously, this all depends upon the whole randomness. The whole idea of instant communication or anything of that sort all depends on the idea that these particles are supposed to be having completely, totally random particles. Like if you had a fountain of knowledge where you can know everything in the universe, I guess you could say the generic view of quantum mechanics is that the outcome, whether it's up or down, is completely random. And you would never be able to know whether it be up or down beforehand. But, there's obviously a completely different question which we could ask, is that what if it's not random at all? Supposing, for example, let's go back in time to when we first entangled these particles. One idea that is a little bit less popular out there is that if the spins of these particles were determined, say, when we entangled them, then it would be a mystery. Let's say that Bob goes on when we have A and B, they collide. What if at this moment, this particle B became downward spin and particle A became upward spin? Then obviously, wouldn't be faster than anything, because it would have been decided at that point. But there's not much to, as far as I know anyway, there's no evidence either towards it or against it. It's just that, so to speak, it's only faster than light travel, depending on which view you want to take on whether quantum mechanics is like truly random or if it just appears random. If that makes any sense. Anyway, I've probably spent way too long on this topic already, so I'm gonna uh, close out this. And the next video will actually be about calculus and hopefully why we even care about it in quantum mechanics. Anyway, see you next time.